Assalamualaikum. My name is Muhammad Afidine bin Muhammad Lalami. Today I will present the distributed food ordering system. The system manages customer food order using three services: order service, kitchen service, and pickup service. The system is built with Java multi-threading, so each service runs as an independent thread and work concurrently. When a customer order, the order service receive it, the kitchen service prepare the food, then the pickup service complete the order. The system also include a DNS like naming service and replica manager for data consistency. All activity are shown live on the console. This report demonstrates distributed process handling, naming resolution, and data replication. Thank you. In this slide, I want to present about what is multi-threading and two-thread in this system. Multi-threading means our system can run multiple tasks at the same time. In default order system, you have two main thread. Each thread is responsible for a different task. The first thread is kitchen thread, which is responsible for cooking food. The second thread is pickup thread, which is responsible for completing order. Both three are handled by Java simultaneously. This allows the system to run faster and more efficient. Let me explain the two main threads in this system. First, kitchen thread. Kitchen thread is responsible for cooking food. When this thread runs, it changes the order status to preparing. Then it waits for 3 seconds to simulate the cooking process. After that, the status changes to ready. Second, pickup thread. Pickup thread is responsible for completing the order. This thread waits for 7 seconds. After waiting, it changes the order status to complete. Both thread run separately but at the same time. Next, let me explain concurrent execution. Concurrent execution means running tasks simultaneously in our system. Kitchen tray and pickup tray run at the same time. This means while the kitchen is cooking, pickup is already running. Pickup does not need to wait for the kitchen to finish cooking first. Both start target from the beginning. We can see this in the system output. Kitchen start cooking while pickup start counting 7 seconds. So these two processes happen in parallel, not one after another. Finally, let me explain non-blocking behavior. Non-blocking means not blocking or not stopping other. In our system, if one thread is delayed, other three are not affected. For example, kitchen thread take 3 seconds to cook. At the same time, pickup thread keep running normally. Pickup thread does not have to stop or wait for the kitchen to finish. This is called non-blocking because no thread block another thread. The system keep running smoothly even if one process is slow. This makes our system more efficient and responsive.
Assalamualaikum. So my part is replication and consistency engineer. Firstly, I will say what is replication and consistency. Replication is the process of storing copies of the same data across multiple nodes to increase availability and fault tolerance. While consistency is a model defining the rules for how data updates are propagated and how nodes perceive the execution order of those updates. So for our food ordering system, we choose sequential consistency. This model guarantees a strict order of operations. For example, a customer cannot try to pick up food before the kitchen mark it as ready or as. It also because eventual consistency would allow temporary still mismatch that cause chaotic customer complaints. I will continue at how replication works in our system. So to implement this, our replica manager class execute a synchronous replication loop. To achieve this strict ordering, we build a centralized component called the replica manager. Every time a thread modifies an order status, it invokes the synchronous replicate method as shown in the diagram. This method follows a straight, predictable sequential update path. First, it updates node A, then it pauses for 1 second, simulate network delay, and then it updates node B, and then again it pauses for another second, and finally it updates node C. While this synchronous loop introduces a total latency penalty of 2 seconds, it is the correct engineering choice for our domain. In a transaction-oriented food ordering system, data correctness and prevention of operational errors cannot be compromised for milliseconds level speed. As for consistency model, first we have correctness. Sequential consistency gives us maximum correctness by preventing stale data reads. It guarantees a customer cannot pick up an order before the kitchen mark it as ready. Second, latency. The cost of this correctness is big. Because our updates are synchronous, our replica manager introduced a 2-second total network delay. However, a customer would much rather wait 2 extra seconds for an app update than walk up to an empty pickup counter. And finally, we have fault tolerance. While sequential consistency can stall if a critical node drops entirely, our architecture ensures that if a crash occurs, the remaining nodes securely hold the last agreed upon state. Last, for our food ordering system, data accuracy must always trump over millisecond level speed. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hani bin Wan Daud. So I want to present the part is simulate naming of lookup resolution. In a distributed system, naming and lookup resolution are essential for locating service across multiple nodes. This simulation adopts a structure naming strategy similar to DNS, which means domain name system, which each service has hierarchical name. Next, structure naming strategy DNS like to make easier, which means to make easier to identify and locate service. Each service is given a structure name. Structure name is self-serve node service description. The first structure name is order.restaurant.local. Resources node A, description, order service. Number 2 is kitchen.restaurant local. Node B, kitchen service. Pickup.restaurant local. Node C, pickup service. For this part, lookup resolution process. When a client or service need to locate another service, there must be following steps occur. The first one is client request a service name. For example, kitchen.restaurant local. That means service receive the request. Number 2 is system search to register hashmap using the service name as a key. Number 3 is return the corresponding node address, which means node B. Client request, the last one is client request. For example, kitchen.restaurant.local. The last part is benefit of the approach. The first benefit is structure organization, which means hierarchical name make service easy to categorize and find. Number 2 is scalability, which means new service can be added by simply inserting new entries into the hash map. The number 3 is low latency, lookup, which means HashMap provide one average time complexity for lookup. Number 4 is human readable names, which means DNS like name are easy to remember that memory address. The last one is decentralization support, which means name can be distributed across multiple naming server in real deployment. I think that's all from me. Thank you.
Assalamualaikum and good day. My name is Muhammad Hafiz Aznab and I will be presenting the system integrator and tester. In this slide, I will talk about what programming we use and how many classes are there. In this slide, we're using the Java language programming. In Java language programming, here we have a recent distributed system package. In the package, we have 8 class. Each of class has their own role. First class is the kitchen thread. Second is main. Third is naming service, not order pickup thread, and last is the replica manager class. All of these I will show you the demo and the coding of the system. Okay, in this slide we have 2 screenshots. The first screenshot is the replica manager and the second screenshot is the naming service. In replica manager, here we created 3 nodes, node A, node B, node C, which each node will play their own role. Node A is supposed to represent the order service or the server. Node B is the kitchen server and node C is the pickup server. Next is the second screenshot, the naming service class. In the naming service, we put naming to each of nodes. First, in the registry put here, we put node A name is order.restaurant.local, kitchen.restaurant.local for node B, and pickup.restaurant.local for node C. Each of node has their own name. Next slide. Okay, in this slide we have another 2 screenshot. The first screenshot is node class and the second screenshot is the order class. In the node class, it has a private string node name, private string order status. In this class, the coding shows us that what is the naming status for each node. So whenever node A, node B, node C is currently doing something like preparing, completed or ready, and in this class, then this class will show each status update for each node. Okay, and the second screenshot is the order class. In the order class, it has a private static integer next order equal 101, private integer order ID, private string item, private string status. In this class, in the order class, what it does is this class it shows that each time a customer ordering something, the ID will auto generate and auto increment whenever a new order coming in. It also shows that an item to select whenever a customer trying to select item A, item B, or item C. And the status received, meaning that whenever customer completed the order, the node will receive the order as a status to show us that the order has been received. Next. Okay, in this slide, we have another two screenshots. The first screenshot is kitchen thread class, and the second is pickup thread class. The kitchen thread class serves as the food preparation or food preparation status. We have the status for this class is the preparing. They will display preparing, and another status that shows ready, and then it will display ready. This is mean to that uh, the kitchen thread class, or the node B, the kitchen thread, uh, shows that food preparation status. In the second screenshot, pickup thread, this one works as a to display the status of the food is ready or not to pick up. Like here we have orders dot set status completed, meaning that the order of the food, customer order, is completed. Okay, next slide. Okay, in this slide, we have another two screenshots. The first screenshot is kitchen thread class, and the second is pickup thread class. The kitchen thread class serves as the food preparation or food preparation status. We have the status for this class is the preparing. They will display preparing, and another status that shows ready, and then it will display ready. This is mean to that uh, the kitchen thread class, or the node B, the kitchen thread, uh, shows that food preparation status. In the second screenshot, pickup thread, this one works as a to display the status of the food is ready or not to pick up. Like here we have orders dot set status completed, meaning that the order of the food, customer order, is completed. Okay, next slide. Okay, this is
Okay,
in
the
this slide
main
we have
class.
a screen record of
The
the
the main class here
main
we
class.
use import
This is will be
library,
a
scanner,
definition
and array list.
of the
In this
system.
class,
However,
here we
I am
using
sorry
the
that I
new
do
name
not have
service,
a face to present
the print
uh,
line display,
the
the summary
demo, but there
services,
will be voice included
kitchen
here
service.
that will
Like click
explain
into here, name
each
service
coding.
restaurant.local,
Yeah.
and
Okay.
display the pickup service,
Okay.
which is going
In
to
this slide,
resolve
we have
the
a
which going
screen
to the
record of the
naming service
main
class,
class.
and then which is the
This
pickup
is will be a
restaurant.local node.
of the
Then
system.
here the node A,
However,
node B, and node
I am
C,
sorry that I do
and
not
replica
have
manager node A,
a
node B,
face to
node C, that
present
will shows
uh, the demo,
uh,
but there will be voice included
the
here
node
that will
instead of
explain
the naming service.
each
This
coding.
is the
Yeah.
array list orders,
Okay.
and this is a scanner,
Okay.
which
In this slide,
for
we
the
have
customer
a
to input
screen record of the
data.
main class.
Here we using while
This is will be
while
a
loop.
definition of
In
the
while
system.
in while loop, we have
However,
the display of
I
the
am sorry that
menu:
I do not
one
have
burger set,
a
two
face to
chicken rice, three
present
fried noodles,
uh, the
and
demo,
here
but there will be
we have
voice
the
included
choose
here that
item,
will explain
which for the customer
each
uh, to
coding.
put their
Yeah.
desired
Okay.
choice.
Okay. In this slide,
Then
we
here
have a
is the
screen
if
record of
for
the
choice,
main
if else
class.
for
This is will be
the
a
history.
definition of
Is
the
for us
system.
to
This is for the
However, I am sorry that I do
the
not
owner of
have
the system
a face to present
can get to see.
the demo, but there will
This
be
is string
voice
item.
included here that
We
will
have the burger
explain
set, chicken rice, and fried
each
noodles.
coding. Yeah.
If
Okay.
uh,
Okay.
if
In this slide, we
nothing,
have a screen
if the
record of
customer
the
pick the
main
wrong
class.
number, like here
This is will
1,
be a
2,
definition
3,
of
then it will
the
shows
system.
invalid choice. Please try again.
However, I
Then
am
after
sorry
that,
that
it
I
will
do not
continue.
have a face to
It will shows
present
it will shows the order,
the demo, but there will be voice included here
status of
that will explain
the
each
order.
coding.
Here the order,
Yeah.
new order item,
Okay.
orders are added,
Okay. In this slide, we have
and
a screen
order
record of
created.
the
Here the
main
order
class.
ID. The order
This is
ID
will
will
be a
be auto generated and
of
auto increment
the
whenever the new
system.
order comes in.
However,
Here are the first
I am
food
sorry that I
item,
do not have
food item,
a
and the
face to
status of
present
the food.
uh, the
Kitchen
demo,
thread.
but there
Here
will be
kitchen thread,
voice
it will shows
included
us
here
the
that will explain
status of
each coding.
the food.
Yeah.
And here's pick up thread
Okay.
when the food is
Okay.
ready to
In this
pick
slide,
up.
we have a screen record of the next
Then
is the
I will
last
show
slide for me.
the
In this
output,
slide,
the result
there's
here.
another screen record that will shows you
Then they will see this
display the
distributed
result, the
order
output
system,
of the system.
resolving services,
However, I am
kitchen
very
service
sorry
node
that
A and picker service node C.
this
And we have the menu list,
a screen
burger
record
set,
does
chicken
not
rice,
include my
fried noodles,
face.
and exit.
But there will be my
pick,
voice to explain
the menu on
the demo
whatever
and
the list on the
the
menu.
result
So
of the system. Thank you.
RPA.
Next is the last slide
Here,
for me.
It shows
In this
shows
slide,
us
there's another screen record
status of the food
that will
is.
shows you the
This is
display the result, the output of the system. However,
the
I am
status
very
is now
sorry
ready
that
here. Kitchen order
a screen
101 is
record does not
preparing.
include my
This
face.
is the order ID.
But there will be my
then
voice
be updated
to
preparing.
explain
Kitchen.
the
Says the
demo
order
and
101 is
the
ready. Node A
result
and
of
node
the
B
system.
says
Thank
it's
you.
ready. And the pickup counter.
Next is the last slide for me.
Counter 101
In this
is
slide,
completed.
there's another
And node A is
screen record
completed. Node C
that will shows
updated as
you
ready. Node B completed.
the
order 101 is
display the
completed.
result, the output
And
of
node
the
C
system.
updated.
However, I am very sorry that
order 101
this
is complete or pick
a
up.
screen record does not include my
Okay.
face.
Let us.
But there will
let
be
me pick
my
another
voice
one.
to explain
Put number 2 and enter.
the demo and the result
Now the
of
order
the
has been
system.
created and
Thank you.
yes generate new ID
Next
102
is the last
for
slide
item
for me.
chicken rice.
In
and
this
it
slide,
says order status
there's
received.
another
The status of the order
screen
received.
record
And
that will shows you
here our
the
kitchen order 102 is
display the
preparing.
result, the output of the
Kitchen
system.
says order 102 is preparing, and then node A
However, I
updated
am very sorry that
preparing, node B updated
this,
preparing, and node C updated preparing.
a screen record does
Kitchen
not
2
include my
says
face.
order 102 is ready. Node A
But
updated
there will
ready, and
be
node B updated ready.
my voice
At the
to
pickup
explain the
It says that
demo
102
and
is
the
completed.
result
That
of the system.
Node
Thank
A
you.
updated completed, and node C
Next
says
is
ready.
the last slide for
Why is
me.
ready? Because
In this slide, there's another screen
the
record
preparing of the food is
that
now
will shows
ready.
you
Here the node C updated
the
completed says that
display the result, the output of the system.
order 102
However,
has
I am very
picked
sorry
up
that
or has been delivered to the
a
customer.
screen record does not include my
And then
face.
we go to number 3.
But there will be my voice to explain the demo and the result of the system. Thank you.
And lastly, if you want to
next is the last slide for me.
or we want to cancel
In
our
this
menu,
slide,
we just
there's another
zero
screen
And
record
here
that will
the
shows
order
you
history.
the
That's all for me. Thank
display.
you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Firdaus Aidi bin Abdul Wahab. Number metric SMSKKI4 I will present the trade-off analysis and the conclusion of our system. Let me start with our first trade-off analysis. Trade-based design versus process-based design. As shown in the table, trade are lightweight, share memory easily, and low overhead. Processes, on the other hand, are heavy and require inter-process communication, which is more complex. For a food ordering system that must handle many concurrent customer requests, trade are clearly more suitable. In our code, kitchen trade and picker trade share the same order object without any extra communication mechanism. That is why we choose a trade-based approach. Okay, for the next, let us compare structure naming DNS like versus flag naming. Okay, flag naming use simple IDs like node 1 or node 2. It is hard to remember and difficult to manage when the system grows. Structure naming use meaningful hierarchy name such as order, restaurant, locker. This is similar to how the internet DNS works. Structure naming is more readable, scalable, and easy to manage. In our system, we implemented this using HashMap inside the naming service class. This allowed us to add new service easily, like drink, restaurant, locker, without breaking anything. Okay, now the most important trade-off: sequential consistency versus eventual consistency. As the table shows, sequential consistency guarantees correctness, no stale read, but it adds about 2 seconds of latency because we update each node one by one. Eventual consistency is very fast, but it's a low temporary mismatch. For a food ordering system, imagine a customer arriving at the pickup counter before the system has updated the status. That would be a bad experience. Therefore, we choose sequential consistency because correctness is more important than speed. A customer can wait 2 extra seconds rather than being told their food is not ready yet. Okay, let me summarize the strength and weakness of our system. About strength, multi-reading allow concurrent processing. Number 2, structure naming make service lookup easy. Okay, number 3, sequential consistency guarantee order status accuracy. Okay, the design is modular. For example, node, order, and replica manager are separate class. For weakness, sequential consistency add latency about 2 seconds per update. Next, if node B the kitchen fail, replication may stale. We have not implemented fault tolerance yet. Currently, only 3 nodes not suitable for very large scale deployment. Last slide is future work recommendation. To improve our system in the future, we recommend 4 improvements, which is first, configurable consistency, which is allow user to choose between sequential and eventual consistency depending on their needs. Second, distributed hash table, which is DHT, replace the simple naming service with DHT to support 100 of nodes. Third, fault tolerance simulation, which is simulate node failure and recovery mechanism. Lastly, graphical user interface, which is GUI, provide a user-friendly screen for real-time order tracking. Okay, for the conclusion. In conclusion, our system successfully demonstrate the key distributed system concept include process handling using multi-reading, naming and lookup using structure, which is DNS like. Number 3, replication and consistency using sequential consistency. The prototype is fully functional, which is meet our CLO2 requirement. All trade-offs were made based on correctness and reliability rather than raw speed which is appropriate for a good ordering domain. We believe this design is suitable for real-world deployment in online food ordering system. Thank you.